So, as a part of my machine learning internship at Art Technologies, I have made this project, Ethereum prediction model using auto-regression integrated moving averages, in short, ARIMA model. So, the objective of this model is to analyze the historical prices of Ethereum and generate predictions for the upcoming days. Uh, For this, we have used a very widely used technique, which is which is combining auto-regressive and moving averages model. These are two separate models, but ARIMA is the combination of these both. Anyway, starting off with the project, the step one will be to install the necessary libraries which are NumPy, Pandas, Matplot, Cbond, NumPy, Pandas for data handling, Matplot and Cbond for visualization, Stats model um for importing some important things like for our model Arima model we are going to import from it, and request is to handle the API request, and Python Binance is for Binance API key. So all these libraries are in the requirement.txt file. Uh, I've installed all of them from the file, imported them all. The cell model used for seasonal decomposed EXLR. We will use them later. So here I'm simply generate. I have made a client here, Binance client, and I'm importing and I'm using my API to fetch some data from the Binance server. So I use a symbol Ethereum because that's obviously I want the Ethereum data. Okay, so I have used the interval as 1 day. We can choose 1 day, 1 hour, 1 month, anything we want according to our requirement. And the start date is 1st January 2020. So from 2020, I'll be getting a data of around 6 years. From present, not 6 years, 5 years and a few months in 2025. Here I am simply filtering out the columns. I need only the 6 column timestamp open, high, low, close, and volume. And I have set timestamp as the index, correct the data types, and store the data into the CSV. I'm actually saving it uh, because I can reuse that data instead of making API calls again and again. So just simply got the data. These are just some testing for the data, there are no null values and all that stuff. And then we have moved to exploratory data analysis. Okay, so this is the overall price versus time graph from 2020 to current date. Uh, Now for the further graphs, I use the data for only 2023, so I filtered it here. This is the price over time from in 2023. These are the rolling averages of 7 days and 30 days. The yellow line represents the 7-day rolling mean, the green line represents the 30-day rolling mean, and the blue line is the normal price. This is the volume graph. These are the daily returns and the distribution of daily returns. This I've used the concept of exponential smoothing models to decompose the data and find out its trend. So the blue line shows the trend of data. Here is the seasonal decomposition, which shows which season of the data is currently active. For example, in this season here active, in this this season active. Now I have to apply stationary testing to check if my data is even stationary or not. First, I simply graphed out the rolling standard deviation, and just by looking at the graph, I I initially concluded that this is stationary data, but that this is what the graph is for, to just observe and think about if it is stationary or not. I thought it was stationary, but we have to verify it using an ADF test. So this is the code for ADF testing. Uh, so by running this ADF test, I found out that it was actually not a stationary time series. So to make it stationary, I checked out if differencing could work. I applied differencing of one, the differencing by one. I plotted it and and again run the ADF test. And this time I found out that uh, the time series is now stationary. So means that differencing by one can make the time series stationary. So how is this differencing value useful for us? So basically the ARIMA model uses three parameters to define its order: P, D and Q. Q we will discuss later, but for now D is the differencing factor, which is the value uh, by which if we apply differencing, the time series will become stationary. So here we apply the differencing of 1 and the time series becomes stationary, so the value of D will be 1. We have figured out the one parameter of ARIMA model. Now we'll move on to now as our time series is stationary. The our time series is stationary. We will move on to training the data, training the model. So here yeah, but before that we need to also figure out what are the P and Q. So here are ACF and PACF plot, which are basically correlation versus lags graph. Now, what are lags? Lags are the previous observation. For example, let's go here above. Okay, no, let's go in a cleaner graph to for better understanding. Yeah, this one. For example, this is the current price of Ethereum. So the previous price here is a lag of the lag for this current price. So this is the lag 1, this is the lag 2, this is the lag 3, this is the lag 4, lag 5, lag 6. Similarly, going back to this is the lag t. We don't know how many lags are there, I don't know, but there are fixed number of lags. So all the previous observations are called lags. So moving again here. So what happens that on every lag the value of correlation changes. Initially the value of correlation is 1, but at some point after remaining at 1, at some point it immediately drops to 0 or near 0. So here we can see that the oh okay, before that the lag at which it drops is called the cutoff point. So the cutoff point of ACF plot is the p value. The cutoff point of the PACF plot is the Q value. So in both graphs, you can see the value has dropped to about 0 at the lag 1. So P and Q will be 0. Now we have figured out all the three parameters of the ARIMA model, which are 1, 1 and 1. P equal to 1, Q equal to 1, D equal to 1. Okay, now we split the data into training and testing data. Now I have made a function. We'll discuss later. Uh, First we'll see this. I have made a list, an empty list for results. I have made a list for parameters. Here we can see this is the predicted or we found out this parameter through our testing. So I have put it in the list. I put some other parameters here: 312, 511, 612, 602. And what I am doing is running a loop and fitting the model on all of these parameters one by one and then storing their results. Now we'll see what the fit ARIMA function is doing. So it is receiving three parameters: P, D, Q, uh, parameters for ARIMA model, then the training data, testing data, and the plot boolean variable to check if it's true, we'll plot. If it's false, we will not make a plot. So I'm using the t-value to determine the trend of the ARIMA model, which trending technique is going to use. Uh, if it's 0 is the trend is C, if D is 1 the trend is C, and else it is N. So here I simply initialize the ARIMA model and fitted it on the training data on the order P, D, and Q. Any PDK value that comes here. I've created a forecast and then I've calculated the RSME and MAP values. Then there's the plot, and then here we are returning the order of the model that we have just uh, trained, the RSME map value, and the model that we have fit. Okay, all the results will be appended here and here. Let's just run this to train again. We can see that 111 on 111 I get the May value 32.27, and but this does not look right because you can see here the testing data is actually going downwards. It's the starting price of testing data is more than the closing price of testing data. So this actually looks wrong, but the MAP value is comparatively better, so we can consider it. Actually, I tried a lot of different parameters uh, using trial and error, and found out that these parameters were some of the best that I got. See here, I have stored graphs for every model that I was trying. So you can see that ARIMA 201, ARIMA 121, ARIMA 111, ARIMA 302, ARIMA 422. I have tried a lot of models, and apparently these were some best one. 111 is not the best one, but we got this from our testing values from our testing, so I am considering it. So now see for 312 it's 32.54, which is not good, comparatively not good, or we can say worse than the 111 model. Now we have 511. It is also worse than the 111 model, but better than the 312 model. Now 612, it's also not much good, pretty much similar than the above model. Now here comes the rail model. This 602 was actually the best model that I found, and it has a great big difference from the other models. Like you can see here, the values are May values are in 32, but this model is 602 is pretty much good. Uh, Wait for it to be completed. Yeah, see, the May value is 17.30. A big, I can say improvement in the model. And boom, here we can see the trend, the prediction is actually going downward, which is nice because as we can see the overall trend of the testing data is going downward. So our prediction are also going downward, which is a good sign. Okay, so now here after testing all the models, I have chosen the best model from the all the trained models, and it also selects the 602 as the best model because it has the lowest map value. And now here I am just simply making a 30-day forecast and plotting it. Yeah, here is the 30-day forecast from 2024 June 4 5 to 2024 5/15. This is the original data, and this is my prediction. And now we can see that this does not look like the data because the ARIMA model works on the historical data. So, for example, if I'm on this point and I want to predict the next point, I will use the data, this previous data. When I'm on this point, I will use this point also, this point, this one, this one, this one, other. And as I keep moving, the uh, the impact of the data point far away from the point we are working on, become lesser and lesser. So when the impact of these points, these blue points were stronger, it was actually going good. But when we move ahead, the impact of the points in this blue line become lesser, so it start to flatten, and as we move on, the impact of this in of these lines become negligible, and the impact of these points become more important to the points ahead. So that's why it got flattened. And as we move on, it may probably flatten more, like we can see here is a little jump, but as we move ahead, it will flatten and flatten more. So this was the model, and it's working pretty much well. Uh, so yeah, that's it.